mass balance problems, blended component. If the fractional conversion of the glucose to lactic acid is 95% and 1000 kilograms per hour of glucose enters the fermenter, calculate the output of the fermenter on the mass basis when the following competing reaction takes place. Glucose produces ethanol and carbon dioxide. What is the yield of the lactic acid? What is the selectivity of lactic acid over the ethanol? Molecular masses of the chemical species participating in the process are given below. This is a problem which is related to the mass balance calculations with the chemical reaction. Because we have chemical reaction taking place here, we have generation and consumption components. We cannot use the general formula input is equal output for going through the calculations. The question is asking us to calculate selectivity and yield from the process, so we have to go back and look at the definition of the selectivity. So if you remember from our in-class lecture, selectivity is defined as the ratio of moles of the desired product divided by the moles of the undesired product. Yield is defined as the ratio of moles of the desired product or products divided by the moles of the limiting reactant fed into the process, assuming that we have 1:1 molar ratio of product to the reactant, and in fact in our process we have 1 mole of the reactant would produce 1 mole of the product, whether it is desired or undesired product. We start our solution with balancing the chemical reactions, and in this case we have 2 chemical reactions. We have 1 mole of the glucose would produce 2 moles of the lactic acid, and this is the desired product, and we know that we have 95% fractional conversion of glucose to the lactic acid. Competing reaction would consume our glucose and it would produce 2 moles of the ethyl alcohol and 2 moles of carbon dioxide. So here we have 5% taking place through the process of generating ethyl alcohol and carbon dioxide. Our process flow diagram would include one input stream in which we have a glucose, and from the problem statement we know that we have mass flow rate of the glucose into the process, which is equal to 1000 kilograms per hour. And in terms of the output, we have 4 components as shown on the balanced chemical stoichiometric reactions. We have lactic acid coming out, we have glucose, ethyl alcohol and carbon dioxide. Since we have a chemical reaction here, we cannot run our calculations using the mass or mass flow rates. We have to convert the glucose, 1000 kilograms of the glucose per hour, into the kilogram moles using the molecular mass of the glucose. So 1000 kilograms of glucose per hour divided by the molecular mass of the glucose would give us 5.56 kilogram moles of glucose per hour. Going through the chemical reaction, dealing with the lactic acid mass balance, we have glucose, 5.56 kilogram moles of glucose per hour entering the fermenter, and now the chemical reaction inside the fermenter would consume the glucose, and based on the balanced stoichiometric reaction we have 2 kilogram moles of lactic acid is produced per 1 mole of the glucose consumed, and because we have 95% conversion, by multiplying the numbers by 95% we would end up with 10.56 kilogram moles of the lactic acid. This is our product produced per hour, times 90 kilograms of lactic acid per 1 kilomole. The mass flow rate of the lactic acid, that's what it is asked in the problem, is equal to 950.4 kilograms per hour. This is output of the lactic acid from the process. The next chemical species inside the fermenter is the ethanol, and this is the undesired product coming out of the process. We have 5.56 kilogram-moles of the glucose per hour being consumed inside the fermenter, and from the balanced chemical reaction we know that per 1 kilogram-mole of glucose that is consuming the process, we will produce 2 kilogram-moles of the ethanol. And we know that we have only 5% fractional conversion of the glucose into the ethyl alcohol, and by multiplying these numbers we have 0.556 kilogram-moles of ethyl alcohol per hour. Now to convert the kilogram-moles per hour into the kilograms per hour mass flow rate, molar flow rate into the mass flow rate, we have to take the molar flow rate of ethanol, multiply it by the molecular mass of ethanol. We would end up with the quantity of 25.6 kilograms of ethyl alcohol per hour. This is the mass flow rate of the ethanol coming out of the process. The last chemical component inside the fermenter is carbon dioxide, and this is the product which is undesired in the fermenter. We start with the molar flow rate of the glucose, 5.56 kilogram-moles of glucose per hour. Looking at the balance stoichiometric equation, 1 kilogram-moles of the glucose consumed would produce 2 kilogram-moles of the carbon dioxide, and the fractional conversion here is 5%. By multiplying the numbers, we would end up with 0.556 kilogram-moles of the carbon dioxide per hour coming out of the fermenter. And because we need to know the mass flow rate of the CO2, we have to multiply our molar flow rate of the carbon dioxide by the molecular mass of the carbon dioxide to end up with 24.46 kilograms of CO2 per hour coming out of the fermenter. To calculate the yield from the process, we take the ratio of kilogram-moles of the desired product, which is lactic acid here, divided by the kilogram-moles of lactic acid that would theoretically would have been produced if there were no side reactions. So the calculated quantity of the lactic acid is equal to 10.56 kilogram-moles per hour, and the theoretical quantity is equal to 11.12 kilogram-moles per hour, and it would give us 95%. So the yield of the process is 95%. Selectivity in terms would be the kilogram-moles of the desired product divided by the kilogram-moles of the undesired product, and 10.56 kilomoles of the lactic acid is produced divided by 0.556 kilogram-moles of the ethyl alcohol produced, and this ratio would give us 19. So the selectivity is equal to 19.